Hi guys, let's talk about the central nervous system. Okay, so a few comments as we begin. We have not always known what the brain does for us. Very intelligent people in the past, like Aristotle for example, noticed that there was a lot of blood flow towards the brain, ergo the brain must be a method of removing heat from the body. This has to be a radiator. Incomplete. Hippocrates, who's the father of modern medicine, like if you become a doctor, you say Hippocratic Oath. Hippocrates was more accurate. He says, "From the brain only arises our pleasures, joys, laughter, and jests, as well as our sorrows, pains, griefs, and tears." And that's a little bit more accurate. Cessation of brain activity is indeed a clinical criterion for death, and our brains are a little different from other animals. There is a lot of give and take in the animal kingdom in terms of brain development, what's big, what's small, what's, how things are all kind of put together. But generally speaking, the areas of our brains which control like our vision, general memory, and motor control of our hands, it's vastly different. Okay, vastly different. Like you can look at an adult chimpanzee using a twig as a tool, and they just can't do it the way that we do it. All right, it looks like a 2-year-old trying to use the same tool. They just don't have that control over their hands that we have. And again, our vision is very unique compared to most other animals. Only some of the other upper primates have vision that can even relate to the quality of ours. Our vision being good for what we do. Other animals have vision that's good for what they do. That's neither here nor there. Alright, 3 major subdivisions of the brain. These are the cerebrum, the cerebellum, and the brainstem. The cerebrum is the upper wrinkly part of the brain. It's broken down into what we call gyri and sulci. Gyruses are the high spots, and sulcuses are the low spots, or sunken in, the deep spots in the wrinkles. And there are 2 hemispheres of this, left and right, and they're connected by this massive nerve that spans the entire internal portion here, from like there to there, called the corpus callosum. It's this massive nerve. You'll see in a second. Now, the cerebrum does indeed make up about 83% of the volume inside the skull, so it's the vast majority volume-wise. But believe it or not, your cerebellum, the hindbrain back here, the cerebellum, by the way, a completely separate brain structure. All right, like I can grab the cerebrum and grab the cerebellum and pull them apart from one another. They're separate. Okay, the cerebellum contains about half the neurons in the brain. So the cerebellum, though small, contains just an absolutely crazy number of neurons. For reasons it has extraordinarily powerful processing capacity, which we'll be talking about here in a little while. And last but not least is the brain stem. Now the brain stem is pretty ubiquitous with the world around us. Like birds have a brain stem very similar to our brain stem, for an example. It's very primitive. The brain stem is sort of shown here in yellow, these lower bits. Okay, these lower bits of the brain, referred to as the diencephalon. Alright, let's talk about the brain. So, cerebral gray matter versus white matter. I believe we've already had this conversation, but the idea is that gray matter, seen here in these wrinkles on the outside, and here in these deep parts that we call the basal nuclei, it literally is a little darker. Okay, deep basal nuclei as well as on the outside of the brain. Gray matter is where you find the nuclei of neurons. Okay, the nuclei of the neurons are found in the gray matter, whereas the white matter is basically the bundles of axons going to and from these neurons. So like the white matter here, these are the axons that radiate out to the gray matter here and bring information to the gray matter there. Okay, you can see the lines here. This is illustrating to you this white matter. The reason it's white is because these are myelinated axons, and myelin is a lipid. And being that myelin is a lipid, it has a light coloration when you look at it. Not unlike if you go to the supermarket and again you look at steaks on the counter and they have a light appearance where the fatty material is. That's a lipid. Fat is a lipid, so is myelin. Alright. Perfect. Okay, so gray matter on the outside and deep on the inside, and then the white matter is in between the two. Telencephalon. Alright, so the cerebrum. Here you can see the right and left hemispheres. Okay, right and left hemispheres. You can see all these wrinkles, these gyri and sulci. And the idea is that the cerebrum is the seat of perception and general thought and judgment. This sort of thing. Like, I do things and I understand things mostly because of my cerebrum. Now, here's an important point to be made. The cerebrum judges what to do, not necessarily how to do it. Okay, what to do, not necessarily how to do it. And that's a very important point to be made because there are other parts of the brain that carry out the jobs that are dictated by the cerebrum. So your cerebrum might decide that you need water. So your cerebellum is going to decide to move your limbs in a specific way to get you to that water, and then other aspects of your nervous system will be involved as well. We'll get there. I don't want to jump too far ahead. Alright, here you can see the gyri and sulci. The gyruses are high spots, the sulci are the low spots. And here specifically you can see the corpus callosum. The corpus callosum is this big nerve. You can see it coming across the other way here in a different section. The corpus callosum is a massive nerve that connects the right and left hemispheres of the brain. You need to probably at some stage in your life go and look up medical procedures where they've cut the corpus callosum. Some of the side effects are just wild. Some of the things that this causes are pretty fascinating. Basically, we will go in and slice the corpus callosum when people have really extreme epilepsy, for an example. And it's a useful medical procedure, but there are some weird side effects. Not bad ones necessarily, just fascinating. When the two sides of the brain can't communicate, strange things happen. So again, this would lead to communication between the right and left hemispheres. Alright, the lobes of the brain. Alright, so there are 5 of these. Frontal, here. Parietals, on either side, or on either side of your head. The occipital lobe, single in the back. The temporal lobes, one on either side, and they kind of stick out like so, and they cover the insular region. Insula, shown here. Alright, so what do these do? What I need from you is the following. I would like for you to know that your frontal lobe is sort of your seat of social judgment, of mood, of voluntary function, all that fun stuff, okay? So, basically, who you are as a person is your frontal lobe talking, okay? So, like social judgment. You, at some stage in your life, have seen someone you don't like. And the reason you didn't walk up and punch them in the face is because your frontal lobe said that would be a mistake. That there would be repercussions that would be bad for your future. Okay? Your frontal lobe basically is who you are as a person. This is a very important concept. Yeah, that'll do. So, parietal lobes. The parietal lobe seen here, and then again another on the other side, deals with general sensory information like taste, for example, is a really good point to be made here. Taste, let's not complicate it. Let's just say taste and general sensation for the parietal lobes. Occipital lobe is primarily focused on vision. The idea is that your optic nerves coming from your eyes come into the brain at the front, they transverse through the brain to the occipital lobe, and then it's in the occipital lobe that your visual processing occurs. So you see things because your occipital lobe processes information from your eyes. Temporal lobes, seen here. Okay, the temporal lobes primarily with hearing. Smell is interpreted in the temporal lobes. Now I've got learning and memory here, but this is a little complicated. Let's not say that just yet. It's because, the reason that's shown here is because the temporal lobes overlie some parts of another aspect of the brain called the limbic system, and it's kind of hard to separate the two because they are so close together. So we'll talk about the limbic system separately. And then last but not least, of course, is the insular region, and the insular region is what helps us to understand spoken language. So when you do a PET scan on somebody and you look at what parts of the brain are active, when you're speaking to someone and they are grasping what you're saying, the PET scan will just have the insular region just lighting up like crazy. That's how we can tell what a lot of this does, is by experimentation using very special scans of the brain. Or alternatively, what we've done in the past is people that have had traumatic brain injuries and we know where the injury is, the problems that they experience as a result of that help us to understand what those parts of the brain did beforehand. Famous example, I invite you to go look, you should pause this video and go look up Phineas Gage. Phineas Gage. Phineas Gage was a tamping man for a railroad, and long story short, he was setting some nitroglycerin, if I'm not mistaken, and he had a big metal rod. They were like building a tunnel for a train to go through. This big metal rod, and the metal rod detonated the nitroglycerin, and it shot it through his head. This metal rod goes right through his head. So from underneath his chin, so right to the side, right at the top of his head, and destroyed his frontal lobe, man. Just tore it to shreds. But apparently, you know, he was totally fine. Like, he was conscious afterwards, and he healed and was completely normal. Well, he healed and was alive and able to do general things. Like, he was a different person. His wife left him, said he became violent. He was a totally different person because his frontal lobe had been damaged. But he was still living. You should go look it up. It's a wild ride. Alright, the diencephalon. So the diencephalon is made up of the following parts. These are the hypothalamus, seen here in this area. The thalamus, the middle of which is seen here. The thalamus is actually these two masses. They look like this, okay? They got a little connection point between them, and then there are these two balls, like so, ovoid masses. You can see this here. This is the thalamus, okay, connected by a little piece in the middle. The thalamus seen there and here, and then the pineal gland, which is kind of in the back here. If you pull the cerebrum and cerebellum apart, the pineal gland kind of dangles down like the uvula in the back of your throat. So it's kind of separate between the cerebrum and cerebellum, the pineal gland. Hypothalamus, thalamus, and pineal gland. And I've got some general functions for these here. Let me see. Yeah, I've got some general functions for these here, but I'm just going to run through them bit by bit. Alright, what I want you to know about the thalamus is that it is deep in the brain and it's made out of gray matter. Okay, it's definitely made out of gray matter. And what it does is it serves as a gateway between the cerebrum, the cerebellum, the spinal cord. Basically, think about the thalamus as the mail room in a building. Mail comes in, and the mailroom sends it to whatever office it needs to go to, and then if that office has a response, it goes to the mailroom, and the mailroom sends it to wherever it needs to go. Alright, so this is like inter-campus mail on Shelton, okay? It allows for information to come to and from different aspects of the brain, so it is a processing center in that information comes in, and it has to decide where it goes. Okay, so that's the thalamus. The hypothalamus is far more impressive. Okay, the hypothalamus is down here in this area above the pituitary gland. It sort of controls part of the pituitary, and below the thalamus. Yeah, that'll do. There's a nice picture. I like these a lot. So that's showing the pituitary gland and the hypothalamus. And the hypothalamus has a variety of very fascinating functions from my perspective. So hormonal secretion by controlling the anterior pituitary gland. Well, hang on. Let me say this. Here's a grand statement. The hypothalamus controls all autonomic function. Let me say that again. If it's regulatory, if it's a feedback mechanism, if it's homeostatic, the hypothalamus controls it. That means that the hypothalamus regulates and is the control center for your autonomic nervous system. That means that the hypothalamus is the control center for your endocrine system. It runs the show if it's regulatory. Okay? If this is keeping your blood sugar where it's, well, within reason, but let's be more specific. Keeping your blood osmolarity where it's supposed to be, that's the hypothalamus, man. It's running the show in terms of all autonomic function. Okay, now then. Alright, controlling hormone secretions. Because your hypothalamus controls the anterior pituitary, what that also means is that it controls the release of growth hormone. Thus, it regulates growth. It controls your general metabolism, reproductive drives, stress responses, like oxytocin is made here, for example. All of this is driven by the hypothalamus. Generalized autonomic effects. Heart rate, blood pressure, the movement of your intestinal tract, even your pupil size. Your hypothalamus controls the autonomic nervous system, so it controls the level of vasoconstriction and vasodilation of your blood vessels. That's a short way to say that it controls all thermoregulatory activities. Okay, so your body's temperature is driven by your hypothalamus. Food and water intake. Have you ever had a craving? When you have a craving for something, that's your brain saying, we really need something. And your hypothalamus is like, oh, I can detect that. Let's go get it. Your hypothalamus is actually the closest connection point between your brain and your general bloodstream, because your hypothalamus is constantly testing your blood to make sure all the chemicals are there that it needs, that your body needs to survive. I'll give you a little example. So, my friend Nancy, I may have mentioned this before, but Nancy is a super cool person. But when she got pregnant, she'd have been a vegetarian for most of her life. When she got pregnant, she immediately became a carnivore. She said that she'd walk past like meat in the supermarket and just have these primal urges. That was her hypothalamus, right? That was her hypothalamus saying, "Hey, you know, you need this specific stuff. You should probably get it." Yeah, perfect. Even like your drives for thirst, like when I'm sitting here and I'm talking, so I'm dry mouthed. But the idea is that when you are thirsty for something, that is your hypothalamus saying, you probably need some water. And last but not least, last but not least here, we're going to ignore this for time being, rhythm of sleep and wake. So your hypothalamus, let me check the camera. Yeah, okay, perfect. Your hypothalamus controls your pineal gland. So here's the pineal gland there. Here's the pineal gland there. The pineal gland regulates melatonin release, and thus you're sleeping and wake. But the trick is that it's working at the behest of the hypothalamus. So the hypothalamus determines when the pineal gland secretes melatonin to help you sleep. So the hypothalamus is in control of sleep and wake. It is completely in control of sleep and wake because it is in complete control of the pineal gland. Seen here. Seen here. Perfect. The cerebellum. So the cerebellum is considered your hind brain, and it is a completely separate brain unit. A little independent brain in form and function all to itself. It's got this neat structure internally. Like if you take this and you turn it up on its end, it looks like a tree. It's called the arbor vitae. Okay, the white matter looks like the limbs, and then the gray matter looks like leaves. It's the arbor vitae, that means tree of life. Kind of a fascinating structure. And if you look at this, there's very little white matter, but piles and piles of gray matter. And this is indicative of the processing power found here. So the cerebellum has about 100 billion neurons. 100 billion neurons internally. About half of those found within the brain. And it gives it extraordinarily powerful processing capacities. Alright, so what does the cerebellum do? So the cerebellum monitors all motor coordination. So it gets information from your proprioceptors, gets information from general muscle stretch, gets information from your eyes, and it'll set your body into what I'd like to consider an autopilot mechanism. So how many times have you decided you need to go from here to there, and you get up and you do it, but you're not actually thinking while you're doing it? Like, I could get up, I could carry this camera, and I could walk around my house and do all sorts of things, and still be explaining to you what the cerebellum does, because my body is being controlled by my cerebellum, whereas my cerebrum is telling you about the cerebellum. What in the heck? It's a wild way to describe it, but it's the truth. You've driven somewhere, you have walked out to your car and not remembered anything about it. You were daydreaming. That's your cerebrum doing other things while your cerebellum takes you where you need to go. So by monitoring your motor coordination, this is very important. Think about the mathematical skill involved in this, all right? So the ability to like walk up steps and put your feet in the right places so you don't fall down, that is all cerebellum. All cerebellum. Alright, and then there are other aspects to this as well. Evaluation of certain sensory inputs. So, like, I can tell you what this paper with this, like, I can tell you what things probably feel like by seeing them. That's actually done by the cerebellum. Timekeeping. So, imagine trying to hit a baseball. The ball is coming to you, you see the ball, and your ability to swing the bat and put it right where it's supposed to be, that is all dictated by the cerebellum. The cerebellum... What was I going to say here? Oh, it's like an out-of-body experience. Like that ability to stand up and hit that ball, it's very much an out-of-body experience. You're not thinking about it, it just sort of happens. That's because the cerebellum controls it. Alright, let me restart video. And back to hearing. So your ability to distinguish between very similar sounding words, that's somewhat determined by your cerebellum, and then that information is relayed back to your cerebrum. And even planning and scheduling tasks. Like how many times have you been sitting somewhere and you realize, oh my gosh, I'm supposed to be doing something. Like the other day when we were doing some Zoom meetings, I'm sitting there and I'm like, oh my gosh, I'm supposed to be doing a meeting. That's my cerebellum reminding me, basically, that I have things I'm supposed to be doing. And it's been shown that kids, especially that have extreme ADHD, where they can't focus, that's a cerebellar issue to some degree. So the cerebellum is mildly smaller by comparison to other kids, which is kind of neat. Alright, the limbic system. Boy, do I like the limbic system. This is super cool. So limbus means the ring, limbus. And the limbic system looks like a ring that surrounds the thalamus, the hypothalamus, and the pituitary gland. It's not actually a ring. If you take this and turn it on end, it looks like this. You have your amygdalae on the outside and the hippocampi inside of that, but all the same. So what are our parts here? We have a cingulate gyrus here, right above the corpus callosum, the cingulate gyrus. And the cingulate gyrus is involved in the expression of emotions through gestures. So you probably know someone who really, really talks with their hands. They really just use a lot of gestures. That's an active cingulate gyrus. All right, they really talk with their hands. That's an active cingulate gyrus. Your hippocampus, right? The hippocampi kind of come out into the temporal lobe a little bit there. That's when we said the temporal lobe has some function in like memory and emotion. But it's the limbic system. The hippocampus is involved in memory, specifically the conversion of short-term memory into long-term memory. Like we see when Alzheimer's patients show a loss of short-term memory, we tend to be able to look at the brain and see destruction in the hippocampus. And the hippocampus is kind of fascinating because this is the only part of the brain where you can have mitotic neurons. So there are neurons that are being made here because you're learning new things. That is memory. Hippocampus, very fascinating. And then the amygdala, one here, one there, amygdalae. The amygdalae are involved in what we call facial expression interpretation and emotion. Now, this is fascinating. It turns out that your amygdalae don't fully fuse into the brain, into the hippocampus, and become functional in their maximal state until you're in your late teens. So what that means is, if you recall back when you were younger, you might have, spent time with people that weren't necessarily good for you, and maybe your parents or guardians or somebody was like, you shouldn't hang out with that person. And you're like, oh, it's fine. That's because your brain wasn't fully functional yet. Okay, you look back and you're like, God, I was dumb. Because your brain wasn't yet fully functional. The amygdala had not yet fused to the hippocampus. Ergo, you could not interpret what we call trustworthiness levels. Like, you have seen someone, like you've been introduced to somebody and you knew immediately, we're going to be friends. Or immediately, oh no, this is a bad person. That's your amygdala. Okay, that's your amygdala talking. Perfect, yeah. All right, and then the fornix seen here just kind of links everything else together. And sometimes, depending upon what you're looking at, they'll link in the rhinocephalon, which is kind of this lower portion down in here. The rhinocephalon is what helps us interpret smells. And this is one of the reasons that smells tends to drive such a strong emotional response. Like, how many times do you walk into a room and think, oh, wow, it's pretty neutral in here? No, it's either good or bad in most cases because you have these strong emotional responses because the rhinocephalon is tied directly into the limbic system, which is the emotional memory seat. Okay, perfect. Let's see, limbic system structures, gratification and aversion. Yeah, all of this boils down to your body trying to protect you. Okay, so you'll be driven towards things that make you happy and elicit good responses from your memory banks. You're driven away from things that could potentially hurt you or that have bothered you in the past. And I mean, this stuff can be really powerful because the limbic system is like wrapped around the hypothalamus, and the hypothalamus controls all of your general autonomic function. This system can just play all kinds of hell with the way your body works, man. You just won't believe it. So think about, what do I want to say? Let's do emotional stress. So think about emotional stress. You have to get up in front of a group of people and give a speech. How do you feel? All right? Palms sweaty, maybe hands shaking. Sometimes you just can't get the words out. You can't speak. You can't get the words out. You're yelling at people. Yeah, it's all tied into this, man. This is a big date. You go, you ask somebody out. When you're a kid, you're really freaking out. big meetings, you get nervous before big meetings. Even me, like I get ready to teach a new class, I've never met any of the students, I get a little, oh, here we go, let's go do this. It's all tied into the limbic system. It's all tied in the limbic system. Because you are mentally like stressing over something, this starts playing hell with your autonomic nervous system. Ergo, you're going to have sweat, you're going to be breathing heavily, and fascinatingly, this causes the release of adrenaline to protect yourself. A fight or flight response is what we're seeing here. Causes the diaphragm not to be able to regulate itself smoothly. You have what we call recruitment synchronicity from chapter 9. So you can't control the diaphragm well, so you're either like, you can barely get the words out, or you're yelling at people. And this is how this all fits together, man. That's how this works. It reminds me of the Cofferdam girl, which I don't think I've ever mentioned to you before. But I'll tell you better now. I went to a big scientific lecture one time in Salt Lake City, Utah. All right, and while I was there was a young lady who got up on stage, and she was talking about cofferdams in Australia, of all places. Now, let me first say this. Nobody cared. All right, nobody really cared. There might have been 3 or 4 people in the room that were really just in love with this conversation. Everybody wanted to see her do well, but boy, she freaked out. She tried to use the laser pointer, and it was like, couldn't control it because of recruitment synchronicity. She didn't have that smooth delivery that you look for. She couldn't get the words out. Her voice wasn't working because of recruitment synchronicity not allowing her to control the volume of her voice effectively. She began to cry a little because the emotional overtake of all this, because all of these limbic system centers are tied into the autonomic nervous system. And it can just play all sorts of hell with the system, okay? Now, a couple of more points to make, and that is psychosomatic illnesses and vasovagal responses. I used to work with a terrible human being. I mean, he was just a bad person, okay? Through to his core, bad person. And he would just make our lives miserable. And every day I woke up and I knew I had to go to work, I would feel like I could just throw up everywhere. I felt so sick. So sick. And there was nothing wrong with me. I just didn't want to be there. So my body found a way to get me out of it. And that is psychosomatic illness. I'll give you another example. So my lab quizzes in anatomy, they are simple from my perspective, but some people find them very nerve-wracking. And I had a girl when I was teaching elsewhere, and she said at the end of class, she said, you know what, this class has been the best diet I've ever been on. I've lost like 15 pounds. I was like, okay, why is that? She said, because I have an upset stomach every day before lab because I'm so nervous about quizzes. That's psychosomatic illnesses. And then, of course, there are indeed vasovagal responses. So a vasovagal response, someone might say, hey, I've got terrible news. You got to sit down. Why they don't want you to sit down? Because if you pass out, which can happen when you get bad news, they don't want you to hit the floor from standing. Okay, they want you to be in the chair to start with. A vasovagal response is basically when your brain's like, okay, lay the bad news on me. And you get the bad news, and your brain goes, okay, well, we're going to take a break now, so let's drop our blood pressure, and we're going to pass out for a little while. That's a vasovagal response, passing out from bad news. It's pretty wild. And let's change gears a little bit and talk about protecting the brain. So the brain is protected through a variety of means. The skull, the meninges, cerebrospinal fluid. The skull is incredibly important here. This is that hard, bony structure on the outside. It's the main protective structure, if you will. So obviously that's important. But we're going to talk at length about the meninges and the cerebrospinal fluid because we've already talked about bone. Okay. Now, meninges, this is a set of membranes that cover the brain, and cerebrospinal fluid is a fluid found in the cranial cavity. Alright, the meninges is broken down into 3 parts. These are the dura mater, the arachnoid mater, and the pia mater. Dura, arachnoid, and pia mater. Now, dura mater means the durable mother. Okay, mater is mother, but that's neither here nor there. It's very thick and very strong. Alright, the dura mater is basically attached to the skull itself, and it forms this really strong connection between the skull and the membrane. Okay, the dura mater is like attached to the skull. It is on it, around the brain. The dura mater is not on the brain. It's attached to the skull. And then let me skip one and go to the pia mater. The pia mater is on the brain like skin on a grape, man. It is attached. So you got dura mater on the skull, you got pia mater on the brain, and a space between the two. The space between the two is filled with what we call the arachnoid mater. You can probably guess what this looks like. arachnoid mater? It's a spider web, okay? It looks like a series of web-like structures made of elastic filaments, and the idea here is that as you move around and do the things that you do, your brain can kind of bounce around inside the skull, but be restrained by the dura, arachnoid, and pia mater. The dura mater attached to the skull, the pia mater on the brain, and then the arachnoid mater sort of suspending everything in place. And yeah, that's how that works. It's a pretty neat system. Cerebrospinal fluid. So cerebrospinal fluid is made at special areas called the choroid plexus, the choroid plexus. Choroid plexus is lined with special cells called the ependymal cells, which are in fact ciliated. So these structures make cerebrospinal fluid, and then the cilia beat and push the cerebrospinal fluid from one place to another. They say you can actually pick up a mild beating sensation from the movement of cerebrospinal fluid. Okay, so cerebrospinal fluid is basically a filtrated blood plasma. That's a fact. Let's see, made by ependymal cells at choroid plexus. It flows by its own pressure via cilia. Yeah, okay, so let me make a couple of points about why this happens. Alright, first comment. This does indeed cover the external surface of the brain, and it flows over. I bet I got this whole slide on this. I do. Let me just say this, and then I'll move on to the next slide. Your blood chemistry is so variable and crazy. I mean, your blood chemistry changes from moment to moment. And if your brain was exposed to these crazy variations in blood chemistry, it would be unhealthy for the brain, generally speaking. So what we have is what's referred to as a blood-brain barrier system I'll be talking about shortly. And these ependymal cells are closely associated with this. These choroid plexi are closely associated. Alright, so what does the cerebrospinal fluid do? Buoyancy, protection, and chemical stability. Alright, let's do buoyancy first. So the cerebrospinal fluid causes the brain to be what we call neutrally buoyant within the skull. That means the brain neither floats nor sinks. It just kind of hovers in place. So it's held in place by suspensory ligaments from the arachnoid mater, and the buoyancy from the cerebrospinal fluid keeps it kind of floating. We basically just don't want the brain to touch the skull. If the brain touches the skull, this is very, very bad. That's a concussion. Alright, so how do we prevent that? Well, we don't want it floating up and touching the top of the skull, and we don't want it sinking, so we have this neutrally buoyant cerebrospinal fluid that fills the cranial cavity, both in the brain and around the brain, to keep it from floating too high or sinking too low. And further protection, when the brain shifts forward, it has to push cerebrospinal fluid out of the way, or alternatively the brain shifted back. It would have to push cerebrospinal fluid out of the way, and what this will do is that movement of fluid works like a shock absorber on the brain and keeps it from moving too much. Again, this is a great way of decreasing the risk of concussions. This is a terrible thing to say, but you should know it's just facts. Like shaken baby syndrome or shaken child syndrome, the kid's shaken and terrible things can happen. But this is basically a response to the brain striking the skull and leading to concussions. All right, and last but not least, chemical stability. So the idea is that the cerebrospinal fluid washes across the brain and moves hormones, moves waste products, moves whatever the brain needs to move. The cerebrospinal fluid can carry it from one place to the next. Can move all sorts of things around. So yeah, cerebrospinal fluid. You can see these ventricles here in the brain. These are all openings. This is all open within the brain itself. They are filled with cerebrospinal fluid and have their own choroid plexus for the manufacture of that cerebrospinal fluid. Alright, blood supply and the blood-brain barrier. Let me check my camera real quick. Perfect. Alright, so blood supply. The blood is indeed a potential source of toxins. The blood is a potential source of bacterial infection. The blood's a potential source of viral infections. The blood's a potential source of all sorts of problems. So what we have to do is we have to strictly regulate what comes in and what goes out. We have what we call a blood-brain barrier. A blood-brain barrier. Primarily, this is going to involve all the capillaries of the brain, capillaries of the choroid plexus. What will go on here is you have these astrocytes that wrap around these blood capillaries in the brain and force them to make tight junctions so that they're not very leaky. What this will, in essence, do is make these cells capable of selecting what products come into the brain and what products go out. And even the astrocytes themselves have these little feet, basically, that touch and hold on to the capillary. So if anything's trying to come out of the capillary, they are testing it to make sure it's what's needed. So we very, very tightly regulate hormone levels, amino acids, ions, whatever, from the blood to keep the brain like a hardcore laboratory environment. It's well protected. Yeah, that's perfect. And so this is very powerful all over the brain. Worthy of mention here is that it is quite permeable around the hypothalamus. We refer to this as being the vomiting center. The idea is if you ever eat foodborne toxins or something like that and it gets into your bloodstream, your hypothalamus can detect this and lead you to get very, very sick very quickly. I trust that we've all been on that old-fashioned 24-hour miracle diet. So if you were to consume foods that have some sort of toxin within them, your hypothalamus would detect this and lead you to completely void your bowels and throw up everything from your stomach. Basically just as an emergency protective measure. Works like a charm. Now some things can get through the blood-brain barrier with great ease, not just at the hypothalamus but everywhere. And this sort of explains our long-term relationships with them. Like alcohol is a good example of this. Alcohol can shoot straight through the blood-brain barrier. That's why we have such a long relationship with alcohol. Caffeine and nicotine. I mean, how many times have you seen somebody that's like that smokes and they're really stressed out and they're shaking, and then they get the cigarette and they take a good puff off that thing, and then 10 seconds later they're perfectly fine. This stuff gets into the bloodstream directly through the stomach for alcohol and through the lungs with nicotine, goes straight to the brain within 1 minute, and affects brain chemistry. So these are quite powerful. Basically, lipid-soluble things are quite powerful at getting into the brain. And then, of course, oxygen and carbon dioxide. Oxygen and carbon dioxide are just so small, they can meander through the blood-brain barrier with great ease. Yeah. Okay. It's perfect. And, let's see, I don't know how much of this I really want to do. Again, I'm trying to keep these lectures simple for you. Like, I love talking about the sleep cycle and how sleep works and what dreams are. It's pretty fascinating. But if I'm being honest, I don't test on it. Look at that handsome boy. Oh my gosh. Yeah, I just don't test on it. I'll say a couple of things. Sleep is absolutely mandatory. Like, we have artificially kept people and animals awake, and the animals that we've kept awake for long periods of time, they will die. People become non-functional. Your brain must go into restorative mode, into what we call REM sleep. You can see the eyes rapidly moving here. That's REM sleep. You have to go into this REM sleep, basically convert short-term memories to long-term memories, and clear out what I would consider your RAM, your random access memory. Like a computer has RAM and then a hard drive. When you sleep, it's like hitting save and saving something from the hard drive out of the RAM. It's very important. So pulling all-nighters before tests is a terrible idea because your brain's going to be in like limp home mode or something. You're going to have all your random access memory full, and you're not going to have converted that into long-term memory. This also explains why babies sleep a lot. Think about a newborn. Everything is brand new to them. So every sight, every smell, every taste is brand new to a newborn baby. So they have to sleep constantly to convert that short-term memory into long-term memory. It's an adaptive process. Alright, so degenerative brain disorders. Alzheimer's, Parkinson's, Huntington's disease, and Lou Gehrig's disease. Folks, if you live long enough, you're probably going to have Alzheimer's. It's just facts of life. People over 65, about 5 to 15%, so relatively low rather. But then once you're in your 80s, the numbers just skyrocket. So what are the symptoms of this? Memory loss, attention span shortness, disorientation, loss of language at the extent, so as we progress here, as the brain is destroyed, you can lose the ability to speak, and then very prevalent irritability, mood changes, some hallucinations, and confusion. So I don't mean to make light of this, but I would like to tell you a little bit about my grandmother whom suffered from Alzheimer's. She was just a funny lady, so these are funny stories. She didn't mean to be hilarious all the time, but she just was, even in late stages of Alzheimer's. Alright, memory loss. Especially the conversion of short-term to long-term memory. We would go and see my grandmother, and she'd be like, "Oh, John, it's so good to see you. Oh my gosh, it's so nice. Like, hey, Grandma, can I get you something? Well, I'd love a cup of water. You know, if you can do that, that'd be great." So you go get it. And you come back, and she goes, "Oh, John, you came to see me. That's so great. I can't believe you. That's so nice of you." And I was like, "Hey, yeah, and I brought you a cup of water." And she goes, "Oh, I need a cup of water." All right, so this was my grandmother. Short attention span. I remember my mother was in the hospital one day. My grandmother says to her mom, "Linda, boy, I just love some music." She's like, "Well, we can't have radios in here." "Well, would you sing for me? Sing me some gospel songs." So Mom starts singing gospel music to my grandmother. 30 seconds goes by, and my grandmother says, "Linda, why do you always come in here singing?" "Oh, I wish you'd just be quiet." Classic Alzheimer's. Classic Alzheimer's. Disorientation, general hallucinations. My grandmother wasn't completely certain where she was near the end. She thought she was in her house some days. She thought she was elsewhere other days. I just never did know. Irritability and mood changes. Obviously, she would have these shifts. And like one example of this, so while she was in a nursing home near the end, deep stage Alzheimer's, confined to a bed, she was completely certain that there was an entertainer out in the common area of the nursing home putting on a show, and that she wasn't getting to see it because we were all keeping her in the room, and she was ticked. There was nothing happening out there, but she was under the impression that it was. She was hallucinating that it was taking place. She would say that there were birds chirping all night in the hallways, like this wild stuff. This is my grandmother, man. These are classic Alzheimer's symptoms. Classic Alzheimer's symptoms. Caused by a buildup of this toxic protein called beta-amyloid protein, and the breakdown of these tau proteins. It's sort of a long story. It leads to these neurofibrillary tangles. Let me show you. So the axon has internal transport mechanisms, and their structure breaks down with Alzheimer's. And when you break down the internal structure of the axon stops working. And if the axon stops working, the cell's not going to function. So the brain slowly deteriorates, and you lose neural function. Okay, you lose neural function. You can see how big these internal chambers get in late-stage Alzheimer's. Now, we have medication that can slow this down, but we can't stop it. These build up these beta-amyloid plaques, man, it just turns toxic and destroys the brain matter itself. All right, Parkinson's disease. So Parkinson's has a earlier onset. So we're looking at 50s to 60s here. And what will happen is a cessation of function of what we call dopamine-releasing neurons. These dopamine-releasing neurons vastly decrease the amount of dopamine that they let loose, and the dopamine-receiving neurons get very oversensitive, and this leads to a variety of problems, including tremors and like a shuffling gait when you walk, and what they call pill rolling, this grinding of the hands sensation. This classic Parkinson's, leading to overall brain deterioration. Now, we can treat this pretty decently these days. We have two drugs in particular called L-Dopa and Deprenyl. L-Dopa is kind of famous right now because it's a derivative of a rainforest plant that was discovered not terribly long ago. What L-Dopa does is something nothing else can do. This plant derivative is capable of being injected into the body or taken in pill form, getting into the bloodstream, flowing around the blood, passing the blood-brain barrier, and then breaking down into dopamine, which is incapable of passing the blood-brain barrier. Okay, you can't just put dopamine in the bloodstream and get it in the brain. It don't work that way. It's got to get into the brain and then break down into it, and L-Dopa can do this. And then Deprenyl decreases the rate of breakdown of dopamine, so basically we're giving the brain some dopamine to negate the effects of this terrible disorder. Now, we can't stop it, but we can slow it down pretty well. The Michael J. Fox Foundation, they do great research. They fund a lot of research towards treating Parkinson's disease, and they've made really good strides in the past. All right, Huntington's disease. I don't want to say a whole lot about Huntington's disease. I will say that it has a pretty early onset. You get this abnormal protein that's called the Huntington protein, and it builds up and it leads to brain deterioration. Death after diagnosis is pretty quick normally. Just several years. The brain really breaks down fast, and you lose brain function as a result of this. This is actually an issue in a lot of cases of too much dopamine, so we actually use dopamine blockers to slow down the progression of this. And then, of course, there's ALS, or what we call Lou Gehrig's disease. So ALS, Lou Gehrig's disease, is where the person, the brain, everything is completely and utterly normal. Everything's totally fine, except The primary motor cortex, so you're the brain that determines or that brings about voluntary motor activity, the primary motor cortex is destroyed, okay, by the disease. Over time, it's destroyed. So the person's totally fine, except they can't have any voluntary motor outputs whatsoever. So this is Stephen Hawking. He died several years ago. He's now entombed next to Isaac Newton, if that tells you anything. But Hawking was completely here, okay? So he's their body, his brain is completely fine, he can understand, he can tell you all about theoretical physics, but he can have no voluntary motor output. He's completely paralyzed, top to bottom. Yeah, that's Lou Gehrig's disease. So typically a short lifespan after symptoms are diagnosed, because you lose the ability to swallow, to breathe. Without a lot of medical intervention, this can be a major problem. So, yeah. And it's the same story. We have drugs that can slow this down, but we can't stop it. And then, I think last but not least, and near the end here, is strokes. So a stroke is a time issue from my perspective. Let me explain what happens. So a person that's having a stroke, normally there will be a blockage. This can also be a hemorrhagic stroke where you have a busted blood vessel in the brain. But normally when I hear about strokes, they're ischemic strokes where you have a blockage in the brain doesn't receive oxygen to one side or the other, to one spot or another spot, and this causes a variety of problems that are pretty easy to diagnose. Okay, pretty easy to diagnose. We refer to this as the FAST technique. So face, you look at the person's face, if one side of their face is drooping or looks paralyzed, is a good example of the stroke victim. Arms, you tell them to raise their arms up, and if one doesn't really work, that's a good... And we're back. So the camera just randomly decided to die there. So we were on strokes. Face, arms, speech. If you're speaking to someone and they don't seem to be able to understand what you're saying, or you can't understand what they're saying back to you, that's a good example of a stroke. And then the effect is time. The idea is, if you can realize that person's having a stroke and get them to the hospital fast, we can administer broad-spectrum vasodilation drugs and go in and deal with the blockage and really decrease the effect of having a stroke. There are people that have had strokes and they are totally fine, and then there are people like my wife's grandfather, whom was having a stroke and fought people off so he wouldn't have to go to the hospital, and tried to just sit at the house, and he ended up with major brain damage. And it killed him after about a year and a half. So he was totally fine, had a stroke, he really had major brain damage as a result of it. And yeah, that's a stroke. So the idea is, if someone is having a stroke, you get them to the hospital as fast as possible. Drag them kicking and screaming, or else they're going to have major brain damage. And then there's lateralization. So this is a worthy topic. So it turns out the two sides of your brain do sort of different things. I mean, they do the same things, but they do sort of different things. The left hemisphere of your brain is very categorical, very mathematical, analytical. When you balance your checkbook, when you work on math problems, when you understand the deep complexities of what we're doing here, that is the left hemisphere of the brain. The right hemisphere of the brain is very representational, imaginative, musical skill, this sort of thing. All right, insight. I like to think of this as like Mac people. You see a guy with a beret typing on a real typewriter at Publix. That's, right hemisphere dominance. And then, like, all these people here working on the Large Hadron Collider, or like all of you listening to me, assuming that you are scientifically minded, we are all left hemisphere dominant. And the right-handed people tend to be left hemisphere dominant the vast majority of the time. There's a small chance that you can become right hemisphere dominant, however. Very, very small chance that you could be a really, artistic genius and be right-handed. Left-handed people are also left hemisphere dominant the vast majority of the time, but there's an increased chance of having greater artistic skill and focus when one is left-handed. So you could expect great painters like Monet or Mozart, great writer of music, composer, to be left-handed by comparison. And then for some of us like myself, this could be all screwed up. Now, did you catch it? That is not what that says. But I'm here to tell you, when I'm writing stuff out, this is the way it falls. A small percentage of people tend to have a lack of lateralization, so the two sides of the brain are just kind of at war with one another. And that's to some degree my issue here, and it's not really a problem from my perspective. It's just something that I have to deal with. We all have our own issues, okay? This is, again, like 10% of the population. Now, lateralization develops with age, and it tends to be more strongly dominant in males. So males tend to have more lateralization than do females, and this is probably the reason that males tend to have a much higher mortality rate from strokes. When a male has a stroke, if it's on the dominant side of the brain, the result is just catastrophic. It's very, very bad by comparison. All right. And this is a neat little breakdown of different parts of the brain and what they do. It's pretty cool. I invite you to look at this if you'd like. Yeah, and that's got it. This is all pretty neat stuff. I invite you to look at it, but I'm just not going to go there. Okay, so you got a test coming. Get ready.